Hey everyone, Sean here for Lambda School, and in this video we're going to be talking about and going over the binary search tree data structure. So the overview and the goal for this particular video is to start to build up an understanding, a mental understanding of how binary search trees work and what some of their pros and cons are. Again, to kind of start to build up a mental model of how this particular data structure works. With the idea then being that once we get to the programming part of the sprint, we will then take that mental model that we've been building up in our heads and translate that into working code. So the first thing we're going to talk about is to answer the question of what are trees, because a binary search tree is a type of tree structure. So before we actually delve into the specifics of binary search trees, we need to take a step back and talk through what are trees in and of themselves. So intuitively, trees are essentially can be thought of as linked lists, but without the constraint that each node only points to a single other node, right? So if we recall the structure of a linked list, we would have an initial head node that only pointed to one other node, that next node being the next node in the linked list, and so on and so forth. So every node in a linked list only points to at most one other node. And so intuitively, a tree is a relaxation of this constraint. So trees or tree nodes are free to point to multiple other nodes. And it turns out that linked lists in and of themselves also count as trees, just with the constraint that each node only points to a single other node. So in a way, linked lists actually are considered a type of tree. As far as to actually illustrate what we actually mean with a visual, here's an example of what we would call a binary tree. And it turns out trees, when we kind of classify different types of trees, a very common classification is to talk about them in terms of the maximum number of nodes that a single node can point to, right? So with a binary tree, every single tree node can point to at most two other nodes, and hence the name binary tree. Likewise, we might have a ternary tree where a single node can point to at most three nodes, a four-ary tree, which might have a name, but I'm not really sure. But in this case, a single node can point to at most four other nodes, and so on and so forth. And you can probably imagine where this trend continues on for. So let's show some common terminology that is used to reference different aspects or parts of trees. I'm not really going to go over these. If you need to, just pause the video here to either write down these definitions or memorize them, because some of these terms definitely come up a lot, and I will be using them kind of with the assumption that you know what they mean going forward. So back to binary search trees. Binary search trees then, as we can tell from the name, are binary trees, and then a binary search tree specifically has an additional invariant or rule that it satisfies at any given point in time. And that rule is that for any given node, all values in the left subtree are less than or equal to the given node, and then conversely, all values in the right subtree are greater than or equal to the value at the given node. So to kind of more closely illustrate what I mean by that, if we examine the root node in this visual that has a value of 14, if we look at every single node on the left side of 14, in this case the nodes containing 9, 8, 11, 2, and 10, all of those values are less than 14, right? So that entire left subtree starting at node 9, all the values in that subtree are less than the parent node of 14. And this trend continues further down. So if we now look at the tree rooted at node 9, right? Every node on the left side of 9, those values are all less than 9, right? Because we have 8 and 2. Conversely, on the right side of 9, those values are all larger than 9, because now looking at the right side of 9, we have two nodes, 11 and 10, and both of the values there are larger than 9. If we move back up to 14 and now examine the right side of the tree rooted at 14, we have 22, 16, 27, and 18. And all of those values are greater than 14. Right, so the idea then with a binary search tree is that you can pick any node, and at that node, any node on the left side is going to be smaller than the value at the initial node, and likewise, conversely, any node on the right side of the initial node that we were looking at, those values are all going to be greater than or equal to our initial node. And this is going to hold true throughout the entire binary search tree. Again, this rule holds true for every single node in the tree. Okay, so let's take a look at an example binary search tree class. If we were to kind of translate a single node, a tree node, into a class, into some code. Obviously, there's going to be the value, so self.value will be set to some value, and then self.left is going to be the left child of this tree, of the tree at this node, I should say. And so on the left side, it's going to be the root of the left subtree. Conversely, on self.right, on the right side of our node, it's going to be the root of the right subtree. And that's how we might kind of encapsulate the binary search tree class, or a single node in a binary search tree. This might be how we encapsulate that into a self-contained class. Okay, so now let's take a look at an example of if we wanted to check if a certain value exists in our binary search tree. So we might have a contains method on our binary search tree class, and in this case, we might try to pass in the value 10. So we're looking to search through our binary search tree and see if the value 10 exists in our tree. How might we do that? Let's walk through it. So if we call this method 10, the first thing we're going to do is we are going to compare it to the root of the tree. So our initial value 10 that we're looking to compare, we compare that to the root of the tree, the root's value, I should say, in this case 14. Once we do that comparison, we can check to see now whether, or we can easily figure out whether 10 is less than or greater to or equal, greater than or equal to the value of 14. And it's easy to see then that 10, since 10 is less than 14, if 10 exists in our tree, it will exist in the left subtree of our binary search tree, right? Because again, 10 is less than 14. So if it does exist in the tree, it's going to exist in the left subtree. So we are now going to traverse down the left side of our binary search tree. From there, we now compare it to the next node in our binary search tree, 9 in this case. So we compare 10 to 9, and since 10 is greater than 9, now we know we're going to go to the right side of 9, because again, 10 is greater. So if 10 is going to exist now at this point in the tree, it's going to exist on the right side of 9. Now that process continues, we check and compare 10 with the next value in our tree, 11. And since 11 is less than, 10 is less than 11, we know that if it does exist in the tree, it's going to have to exist on the left side, not on the right. And then finally, lo and behold, we arrive at that last leaf node, and we check our initial value 10 with the value at this leaf node, and they happen to match. So now our function could return true to indicate that yes, this input value 10 does indeed exist in our binary search tree. So that's a bit of an example of how we might do a contains check through a binary search tree. So having gone through that example, let's take that as a springboard to kind of ask a few other questions about how a binary search tree works. So some other questions to ask yourself might be, we walked through an example of contains. How would an example of inserting into a binary search tree work? So kind of using the logic that we've just talked about with the contains example, try to see if you can apply that same logic to the problem of now inserting into a binary search tree. So inserting some value into some binary search tree, making sure that it gets to the right part, to a correct spot in the binary search tree, and how might that work? So definitely draw it out and walk yourself through how that logic might work, just like how we walked through the contains method. And then additionally, try to figure out how the insertion would differ from the contains example that we just walked through. And then another question might be, in the contains example, how many elements did we actually have to physically inspect? How many comparisons did we actually have to do as we were going through that contains example? So count that out and figure out, how many, that number that we actually physically checked, how many is that out of the total number of elements in our binary search tree? And then once you figure out that fraction, how does that actually compare to the number of elements we would have to check if we were doing the same contains checking through an array or a linked list? So you have to walk through how a contains works with an array or a linked list, and then compare the number of elements that would have to be checked when you're doing a contains check in an array or a linked list. Compare that to how many elements actually need to be checked when going through a binary search tree. And then lastly, is inserting into a binary search tree more or less work than inserting into an array or linked list? Why or why not? All right, now let's talk about some pros and cons of binary search trees. So kind of as their name suggests, binary search trees are indeed optimized for searching. Right, so one of the pros is that searching for an element in a binary search tree should be significantly more efficient than searching through an array or a linked list. And again, try to prove that to yourself through the example that we walked through with that contains example that we walked through earlier, because that is an example of searching for a specific element in a binary search tree. Again, how would an array or a linked list do it in comparison? A con as a trade-off is that it actually turns out it's not as efficient to insert into a binary search tree as it is with an array or a linked list. And again, if you don't see why this might be the case, try to draw and model it out for yourself. And then lastly, the performance of a binary search tree actually depends a lot on whether the tree is balanced or not. So if you don't know what that means, that would be a good term to kind of look up, what it means for a tree to be balanced. And once you figure that out, we can ask ourselves then, is this generally a good assumption to make? On average, are trees typically going to be balanced? And then when might this assumption be incorrect? And how would that kind of adversely affect the performance of our binary search tree as a result? So again, those are some important questions to ask yourselves to kind of flesh out how binary search trees work as a data structure. And those, again, are kind of important questions to work through and figure out for yourselves. So then, if you still have questions at this point of this video, definitely make sure you write them down, as well as any other questions that might have arisen as you were going through the video. Write those down and be sure to ask them in the live lecture when you get there. So that's it for our overview of binary search trees. And I will see you guys later. Thanks.